we will start about studying how to write the electronic configuration of an atom. So, first let us see what is an electronic configuration. What is electronic configuration? So, it is the distribution of electrons into orbitals of an atom. So, electronic configuration is the distribution of electrons into orbitals of an atom. That is, one atom can have many electrons. Electronic configuration tells us about the arrangement of these electrons. So, we had said that there are two possible ways to write an electronic configuration. Now, this method depicts only two quantum numbers. N and L. But this method gives us all four quantum numbers. So, this is actually the better method, but this method takes less time. So, let us start. The first element in the periodic table is hydrogen with an atomic number of 1. So, hydrogen has only one subshell, that is 1s, which will have 1 electron. We can write it like this, 1s1. So, we will write the principal quantum number and the azimuthal quantum number, and we will write the number of electrons in the superscript. The next is helium, Z equal to 2. So, there is the 1s subshell, 1 electron, and the second electron will come here only in the opposite spin. So, we will write this as 1s2. The third is lithium, Z equal to 3. So, first is 1s. Now, 2 electrons are occupied. So, for the third electron, we need to put in the next subshell, that is the 2s. We know according to the Aufbau principle that which subshell will come after whom. So, the third electron will be placed in 2s, and we will write the configuration as 1s2, 2s1. Similarly, for beryllium, Z equal to 4. So, we have 4 electrons. This is 1s2, 2s2. Now, boron with Z equal to 5. So, we have 2 electrons in 1s and 2 electrons in 2s. Now, there will be 2p. It will have 3 orbitals, 1 electron is filled. So, the configuration will be 1s2, 2s2, 2p1. Next is carbon with atomic number 6. Now, in the 2p orbital, we have seen according to the Pauli's exclusion principle and Hertz rule that we will first have to fill up the single electrons. So, the second electron will be filled like this, 1s2, 2s2, 2p2. Similarly, for nitrogen, we will have 1s2, 2s2 and 2p3. So, this is the half filled configuration of p orbital. 1s2, 2s2, 2p3. Now, if we write oxygen and fluorine, so oxygen will be 1s2, 2s2, 2p4. So, we have 1s and 2s in the similar way, and since all the orbitals has been filled with one electron, now the fourth electron will come in pairing with the opposite spin. Clear? So, we get 1s2, 2s2, 2p4. The next one is fluorine with atomic number 9. So, we will have one electron again paired. So, 1s2, 2s2, 2p5. Now, the next is atomic number 10, which is neon. So, in neon, all the electrons will be paired because it will have a configuration of 1s2, 2s2, 2p6. That is, all the orbitals are completely filled. This is called the fully filled or completely filled configuration. Due to this reason, these elements which have all the orbitals completely filled, that is, there is no single electron, or better to say no unpaired electron. Such elements are called the noble gases. Noble gases. Okay. The neon is the first noble gas. Before this, helium was also a noble gas because this has 1s2. Okay. Helium is also a noble gas. Neon is also a noble gas. These are also called inert gases because they are very less reactive. They almost don't react. These are called inert gases also. Now, this is the configuration of neon, right? Now, if we write sodium, which has Z equal to 11, this will have a configuration of 1s2, 2s2, 2p6, then 3s1. So, for the higher elements, we will not write the full configuration every time because it will take a lot of time. So, what we will do? We will have the configuration of sodium as this: 1s2, 2s2, 2p6 and 3s1. Now, since this is the configuration of neon, we will write this as Ne in a third bracket, and we can write the configuration of sodium like neon with 3s1. Similarly, after sodium we have magnesium, Z equal to 12. We can write it like this: neon 3s2. So, we can write up to the next noble gas with these configurations. When the next noble gas comes, the next noble gas is argon with atomic number 18, and the electronic configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6. This is the configuration of argon. So, when we write potassium, which has atomic number 19, we can write argon and 4s1 like this. So, this way we can write the configurations. Now, till now we had discussed only S and P subshells. Now, D subshell comes from scandium with atomic number 21. So, this will have a configuration of argon 3d1 4s2. We had discussed that the energy of 3d is higher than the energy of 4s. That's why first s orbital will be filled, that is 4s, and after that 3d will be filled. So, calcium with atomic number 20 has this configuration. So, scandium is written like this. Now, from 3d1 to 3d10, we know that D subshell has 5 orbitals, so it can have a maximum of 10 electrons. So, from 3d1 to 3d10, these are called the first row of transition metals. Okay, or the 3D series. Similarly, 4D series and 5D series are also there. Those are called second row of transition metals and third row of transition metals. So, the configuration of transition metals are written like this. This is scandium. After that, for example, we can say iron. Iron has a atomic number of 26. We write argon like this. Argon 3d6 4s2. So, the configuration of transition metals are actually very easy to remember. This argon and 4s2 remains the same, and the number of electrons in the d orbitals increase one by one. But there are two exceptions. These are chromium and copper. Chromium has an atomic number of 24. According to that, the configuration should have been like this: argon 3d4 4s2. But this is wrong. The actual configuration is argon 3d5 4s1. Why? Because if we draw the D subshell 3d 4s. So, if we write like this should have been the configuration. But if we write 3d5, then this is the half filled configuration. So, 4s will have 1 electron. Now, similar case is observed for copper, which has an atomic number of 29. So, the atomic number is 29. So, the configuration should have been argon 3d9 4s2. But this is wrong. What happens? The configuration is actually argon 3d10 4s1. So, five, 6, 7, 8, 9. This should have been the configuration, but it is actually like this. Because this is the fully filled configuration of D subshell. Now, why these cases occur? Because there is one fact that half filled and fully filled configurations are exceptionally stable. So, to attain stability, the configurations occur like these. But what is the reason behind this exceptional stability? Reason behind the stability of half filled and fully filled configurations. Okay. We have seen that for chromium and copper, chromium leaves the 3D4 configuration and attains 3D5 configuration to attain the half filled state. And copper, although it originally has a 3D9 configuration, but it attains the 3D10 configuration to attain the completely filled state. Now, why do they behave like this? It is because the half filled and completely filled configurations have some exceptional stability. Now, what are the reasons behind this exceptional stability? So, there are two reasons. One is the symmetrical distribution of electrons and another is the exchange energy. So, the reasons behind the exceptional stability of half filled and fully filled configurations. The first one is symmetrical distribution of electrons. Okay. So, there is one general idea that symmetry leads to stability. So, anything which has symmetry gains some additional stability. Now, let us consider D4. If we consider D4, then we see that the configuration is like this. If we have D6, then we have a configuration like this. But for D5, we see a configuration like this, and for D10, we have a configuration like this. So, what is the difference? In D4, one orbital is vacant. In D6, one orbital has 2 electrons and the others have 1 electron. So, all the orbitals are not the same. So, they do not have symmetry. But in D5, all orbitals have single electrons, and in D10, all orbitals have 2 electrons. So, they have symmetry. Due to this symmetry, half filled and full filled configurations gain some extra stability. Okay. The second point is exchange energy. What is exchange energy? When two or more electrons have same spin and are present in degenerate orbitals of a subshell, they can exchange their positions and the energy released due to exchange is called exchange energy. So, greater exchange energy means greater stability. Okay. So, let us say if there are 3 electrons, okay, then one can exchange with 2, one can exchange with 3 and 2 can exchange with 3. Okay. So, 3 exchanges will be possible. Now, if there are 5 electrons, so what will be the possible exchanges? One can exchange with 2, one can exchange with 3, one with 4, one with 5. Now, similarly, for 2, the second electron can exchange with 3, 2 can exchange with 4, 2 can exchange with 5. Now, the third electron can exchange with 4, it can also exchange with 5, and 4 and 5 can also exchange between themselves. So, total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 exchanges. So, for a D5 configuration, 10 exchanges are possible. Similarly, for D10 configuration, what happens? There are 5 electrons with upward spin and 5 electrons with downward spin. So, again 10 such exchanges will be possible for the downward spin electrons also. So, D5 and D10 configurations have maximum number of exchanges. So, they will have maximum exchange energy. These are the reasons for their exceptional stability. So, with this we have completed the chapter of structure of atom. Thank you and happy learning.